see what we see. So yeah, that was, I mean, the calculation I was hung up on. It's just, I was thinking about it the wrong way. Like, I should look at this and go, okay, so, I mean, it is true that that's j times f sub k, but really the point is that that's f sub k plus 1, or it's f1 if this is when k is equal to, n minus 1. So like, well, if k is equal to n. So if k is equal to n, you're at the at the nth one, you have j to the n, which is like a constant in our assumption. So anyway, the point is that this is either the next one or it's back to the first one. Technically c, because we assume that j to the n was equal to c in the theorem. And so, but the larger point is that this is the same as one of those in every case. K equals 1 all the way to n. So you've got a sum of determinants, each one of which is the determinant of a matrix with a column repeated. But if you have any two columns in a matrix repeated, the determinant's 0. So that was it. So I got distracted with, I mean, rewriting that as j times f sub k is true but useless, because you wanted to rewrite it in terms of the columns that were there, not in terms of j times a column, which is, not a wrong expression, it's just not helpful. Okay, so yeah, the next paper, there's a variety of different things people have done on this project over the years. Oh, I shouldn't erase that. Oh well. So I think I've showed you more or less, like, we can do calculus, we can do power series. The theory of power series over the algebra is very useful because we can solve a whole manner of, we can set up all kinds of elementary functions. And then, of course, one of the next things on your list, a kind of to-do list of mathematics to understand would be differential equations. So that's the kind of the next thing I went to, partly because I'm aware of the reverse problem, like if I can recast a partial differential equation as a differential equation over the algebra, and I can solve it over the algebra, then I can go back and then I've got a solution to the partial differential equation, which might be...
Yeah, we're trying to get out the main equation.
Right, it might be that inverse problem. So with that in mind, the more differential equations over an algebra I can solve in a nice way, the better. And also as another benefit to this is, like, maybe I can understand regular differential equations more deeply by abstracting it a bit. Sometimes that's a possible way of understanding something more deeply. I mean, when I went to graduate school in physics, Van Nieuwenhuizen said that to really understand general relativity, you need to study, supergravity. So, which is, of course, generalized general relativity. And, there's something to that. If you can understand how to, like, take the regular theory and twist it and change it to something more out there, and you understand more than one different way to do that, then you do have a better grasp of just how special the regular theory is, So I think that is one significant benefit of this paper. So this paper I wrote with Nathan Bedell. Really, we worked out this stuff for the most part in the summer of 2016. A lot of it was known to me before then, but it was in summer of 2016 that it really pinned it down. And Nathan spent the lion's share of his time, I think, working on what we originally called the stupid solution, but also just general Nathan spent a long time thinking about how factoring works over the algebra, and some of those things appear in his papers. He has 3 papers on like pre-calculus over the algebra. As far as I know, they're unpublished, but they are on the archive. I have links to them on my paper, on my page. So I'm going to read the abstract here because this will give us like a bird's eye view of the paper. So what I say is we study the theory of ordinary differential equations over commutative, finite dimensional real associative unital algebra A. We call such problems A-ODEs. If a function is real differentiable and its differential is in the regular representation of A, then we say the function is A-differentiable. In this paper, we prove an existence and uniqueness theorem, derive Abel's formula for the Wronskian, establish the existence of a fundamental solution set for many A-ODEs. We showed that the Wronskian of a fundamental solution set cannot be a divisor of 0. 3 methods to solve non-degenerate constant coefficient A-ODEs are given. Excuse me. First, we show how 0 divisors complicate the solution by factorization of operators. Second, isomorphisms to direct product are shown to produce interesting solution. And third, our extension technique is shown to solve any non-degenerate A-ODE. We find a fundamental solution set by selecting the component functions of the exponential on the characteristic extension algebra. The extension technique produces all the elementary functions seen in the usual analysis by a bit of abstract algebra applied to the appropriate exponential function. On the other hand, we show how 0 divisors destroy both existence and uniqueness in degenerate A-ODEs. And we also study the Cauchy-Euler problem for A-calculus and indicate how we may solve first-order A-ODEs. So that's, you notice nothing about systems of differential equations yet. And let's see here. No, nothing about like the analog of like Laplace transforms for differential equations. That's not been something I've done yet.
Was this paper on pre-calc? Did he get to the FTA over an algebra?
Fundamental theorem of algebra over an algebra? Yeah, that's not. It is. Well, we'll see what the complications are there.
I can see 0 divisors being a big deal.
Yes, 0 divisors are a problem. Excuse me. All right. So let's go here. Now my first section is really just an expansion of the abstract, so I'm going to skip over that. Section 2, Introduction to Calculus. So here you've seen all this already. Definition of what it is to be an algebra, regular representation, the matrix of the algebra, matrix of the map, of the excuse me, element. Hyperbolic numbers, their regular representation, 0 divisors of the hyperbolic numbers. There's the isomorphism to R cross R and its inverse. Oh look, both formulas are here. See, that would have been handy. We worked that out the other day. Some multiplicative. There is another paper. There's a paper by King. I've mentioned this before. We should get that paper in front of us at some point. Just not so much that I'm not saying we need to work through that paper by any means. I just think we should be aware of the results in there as well. Because it actually gives us M sub A for n hyperbolics and n complex numbers, like the best choice of M sub A, and it has some further results on basic issues of the norm in algebra, basically. So here's some multiplicative norm section. We can make M sub A root 2 for hyperbolics. All right, great. Excuse me. I think that corollary 2.6 is a little bit new. Notice that if B is a unit and A is in the algebra, then norm of A over norm of B is less than or equal to M sub A times the norm of A over B. That's a new thought that was not present in the previous paper, if I recall correctly. Then 2.3 is on differential calculus. I mentioned the, deleted difference quotient versus the our standard definition, and the Cauchy-Riemann equations, and you got sum, pull-out constant, product rule, chain rule, power rule. You got the Wertinger calculus that we talked about before, that you can capture Cauchy-Riemann equations by vanishing of the conjugate derivatives. If the function is real smooth and once a differentiable, then you can find as many a derivatives as you like. Equation 11 is super cool in terms of converting derivatives to derivatives with respect to the first variable. So there's that is for a differentiable functions, that is a very kind of, I would say surprising, if you will, relation to love. Again, we talked about this before. I don't know how to, kind of stuck with just homogeneous equations, like equation 12 is homogeneous in the sense that it's, all the terms have order k.
Mm-hmm.
Still don't know quite how to fix that for other orders. But again, those wouldn't be Laplace equations, those would be other. Actually, we will see how to solve differential equations of the algebra of varying orders, but the methods we'll use to solve those will just be like the methods we use to solve differential equations. Like, for example, y prime plus 3y equal to 0. One has one derivative, one has 0 derivatives.
Yeah.
You can solve it,
Yeah, you find characteristic equations.
Mm-hmm. So here's the integral calculus. So basically up to section 2 is just a lightning review of everything we know from previous papers. All right. Now, section 3 is the existence and uniqueness theorem. And but I'll just give you a summary of what happened here. In that summer 16, I was looking at this question, and one of the first things you talk about in the differential equations course but never prove is the existence and uniqueness theorem. For first order differential equations, maybe you remember it. It's like if you have dy dx is f of xy, and you have partial f, partial y is like non-zero at the point, and there's some conditions that have to be added there, then there exists a unique solution. Right? So like if partial f, partial y is 0, then all bets are off. And in their solution means y is a function of x. And there's more general versions of, but the existence and uniqueness theorem for differential equations, it's a standard problem of analysis, and if you study manifold theory or other things, like you'll get to a certain point and then you'll have to rely on this existence and uniqueness theorem. Like it's important. So what this was I was like, okay, well I should try to do that for the algebra. And then so what I did is I looked up the proof of the existence and uniqueness theorem, which is in Nagelsack and Snyder's book, the book you use for differential equations. In fact, in the chapter 12 of that book, in the edition I was using, there's a proof. And through some, took me a while, but I was able to adapt the proof to the algebra. And so that's essentially what this section is my proof of the existence and uniqueness theorem. So here it is, theorem 3.1. So first of all, I also had to introduce the concept of like more than one a variable. See, because differential equations over an algebra necessarily, like maybe you talk about, dw dz equal to a function of z and w. This would be kind of analogous to like in differential equations to do something like dy dx is equal to a function of x and y at the start of the course,
Yep.
But this is a function on the direct product of the algebra itself, you know?
Yeah.
And so that then led me to say, oh, well, I need to make sure I understand partial derivatives with respect to the algebra variables. But you can define partial derivatives with respect to the algebra variables in pretty much the natural way, which is equation 14. And there it is. And so if your g, notice g is from am to a to the k, so we've not talked about that before, but now I'm looking at a function that's from an m tuple of algebra elements to a k tuple of algebra elements, so it's got k component functions g1 through gk. And so I'm extending the definition of partial derivative. Well, anyway, equation 14, partial derivative defined, and then you can straight away get that if you have the differential at p of g on h1 through hm, it's a linear combination of those partial derivatives in that sense. So that's the notion of partial differentiation that I need for theorem 3.1. Let I be compact and star-shaped in A. So compact means, you know, for our purposes here, closed and bounded. Star-shaped means that there's a star center so that you can reach any point in the set from a line segment from that star center without going outside the set. It's kind of what it sounds like. Do you know star-shaped? No.
No, but the way you explained it made sense. Like,
Yeah.
if you have any set.
Here, like here's something that's not star-shaped.
Yeah, you can't draw a line from
Right.
it. Yeah.
But on the other hand, this is star-shaped because if you pick like, you know, say this point,
Yeah.
you can get, of course, anywhere over there from line segment, right?
Mm-hmm.
And you can get as close as you like. I've deleted, like, just,
Yeah.
I could just delete that one line. If I just delete the one line, then you can always like take a shallow enough line to hit a point right above it. So, a lot of things are star-shaped. A lot of things aren't, but star-shaped is really a pretty generous category of shapes to work with, and it's really just a choice on my part. I think you could state this theorem for other things if you wanted, if you just wanted to go through the whatever rigor was needed to deal with the other kind of shape. But star shape was useful to me here, just to make it concrete. So we have, suppose that f from, now R is, now here I is the compact subset, and so if I cross AK, R is I cross AK. So I is a subset of A. It's compact and star-shaped, right? And then R is I cross A. So technically that's a subset of A. A to the K, right? A to the K. So this, I think, would technically be a subset of A to the K plus 1, for what it's worth. All right? And you've got this function, which is from R to where? To A again, right?
Mm-hmm.
Oh. Ooh, I'm actually greedier than that. It's A to the K valued. And I assume that the condition that I need is that this is a differentiable. Which is kind of funny at this point, because I think I'll explain more what that means in the proof, actually. because I mean, technically I haven't really defined a differentiability, unless I just skipped over something. But anyway, the point is the partial derivatives of f with respect to, how do I denote it? Y. So I'm using notation like z comma y vector is an element of this. So y vector is like a vector of a variables. So I have partial f, partial y, j. Come on. Partial f, partial y of z, comma y vector. The norm of that is less than or equal to L. And that's aware for all z comma y vector in R. So supposing that the partial derivatives of the defining function of the differential equation are bounded, and then finally I say, okay, pick an initial point, z naught w naught vector in R. The initial value problem, dy vector dz equals to f of z comma y, with y of z naught equal to w naught, has a unique solution on I. So then there you go. So this is A-ODE, dy vector dz equal to f of z comma y has a unique solution. On R, such that we call that solution phi of z naught equal to y naught. So the phi is going to be a mapping from R to, no. Should be I guess the phi should be mapping from, in this context here, I think phi is going to be mapping from I to AK, if I remember right. All right. Now, well, a second. There's something simmering in between Diego and Matthew. Matthew sounds offended. Shall I? Okay. So, the proof, again, it follows essentially the corresponding proof for the real differential equations, right? And actually, I think this is going to work for a system of first-order differential equations. You notice that there's just a first derivative here.
Mm-hmm.
All right. So the proof is by what's called the Picard iteration, and so the first iterate, you just say y sub 0 is equal to w naught. That's where you start, and then recursively you define y sub n plus 1 of z to be w naught plus the integral of f of zeta yn of zeta star d zeta integration, right? That integration makes sense because z naught to z is a line segment, all right, and consequently it's still in I because I was assumed to be star shaped, all right, and well, I guess I shouldn't quite, I mean, there's a little bit more there than that. If Z naught was a star center, that'd be fine, right? But if Z naught's not the star center, you can get over to the point, you can, I think my proof here might be missing something. Because really, if I'm starting at Z naught, right? And this is the star center, and this is Z. What I should be doing, I'm trying. What I should be doing is like taking Z, going to Z star, and then going over to here like that, you know? The fact that this is star shaped means it's simply connected, and meaning there's no holes. And so the integral calculus we did before, we're also assuming that the function is a-differentiable, which means that it, the integral is independent of path, if I recall correctly, so I can just go integrate like that. The point is, the integral is well defined, and I mean, maybe I should, instead of saying star shaped, I should say the region is such that, you know, any 2 points in the region are connected by a line segment. Okay. I think that's convex, but anyway, all right. So there's that.
Wait, any 2 points, wouldn't they have to be at least 2 line segments? So
Oh, I'm just saying, if my current proof wants to stand,
yeah.
I need to assume that the region is a little bit simpler than just star shaped. Unless I'm forgetting something about the proof, which is possible. It's been a couple of years. Okay, so and then what do? I say, okay, well, this integral, but I mean, I haven't actually defined that integration yet, right? So here's what we mean by that integral. That integral, so the structure of this proof is really different than anything you've ever seen. And all the things you've ever seen in your coursework and everything else I've shown you, we make definitions, right? And then we state theorems and we prove things. I'm doing something really quite different. I'm stating a theorem, and then I'm giving a proof where I'm unveiling what I mean by the things stated in the theorems as the proof is developing. It's a different format than you're used to, right? And if I could ever, you know, I need to submit this somewhere for publication, and maybe they'll make me rewrite it, who knows. I've tried a couple times to publish this, and it's just, I haven't found the right journal yet. But
Were the other 2 published?
the thing with Daniel Freeze got published, not the full paper, but like a subset of it. And the first one, no. No, there's a paper we published from before then, the stuff about the A-Laplace equation. I still haven't showed you the A-Laplace equation, have I? Oh, that predates all this stuff.
Wait, is that the UXX, UV, UI?
It's weirder still.
Oh. Never mind.
A-Laplace equation.
You might have shown that.
No, I have not. I have not.
UX equals VY, that stuff.
It's something weirder still. The A-Laplace equation basically says that you can take the regular representation of the algebra, formally replace the elements of the regular representation by corresponding differential operators, and then the determinant of that thing gives you a differential operator of order n, which automatically is 0 when it operates on any function, any a-differentiable function. So this differential operator of order n, it ends up somehow being some sort of amalgam of like a Laplace equations. I'm trying to think of the a Laplace equation is just the Laplace equation for like n equals to 2. So, as you know, this is the regular representation.
The hyperbolas.
Complex,
Oh, yeah.
a minus, right?
Yeah.
So can take that and go, right, take that, take the determinant of that thing, bam, Laplace operator. This differential operator we call the a Laplacian. In this case, H3. And we proved that if you let that hit any function that is H3 differentiable, it gets you 0. This was Spencer's. Although Lynn says he found it too. I don't know who found it originally. I think it was Spencer. Spencer found this and tried to tell me about it for about a month. And finally, after about a month of him telling me about it, I was like, oh, you read this? And he's like, yeah, I've been saying that for a month. I'm like, sorry, Spencer. I couldn't, because it was just weird enough what he was saying that I wasn't tracking. It wasn't what I was looking for. It wasn't what I was expecting. And this process of switching a matrix of entries to like a matrix of operators just kind of weirded me out. But we should look at this some other time. It's not. Let's look at that some other time. Anyway, my point was Spencer, Min, Belu figured this out. We found a bunch of examples of it, and we gave some talks about that in like 2012, 2013, and then we published a little paper about that. So that's something that's out there. Anyway, so the integral of f star d zeta, you can break up into a vector of integrals of the component functions, right?
Yeah, nice.
And so that's okay. And the thing is, y sub n can be written as y sub 0 plus the sum of the successive differences of the y sub n's. All right? This is important because that means that the uniform convergence of that sum of successive differences is tantamount to the uniform convergence of yn. And uniform convergence of yn would be ever so lovely because then we get to use all of those happy theorems we looked at in the last paper. Right? Because those things adapt here as well. Anyway, so we'd like to show that this series is majorized by a convergent series. All right. So 19, I start with looking at y1 minus y0, which is the integral of, just the integral of f over the line segment. So by the mammal theorem, so the m, so for whatever reason I switched from L to M in the proof, My bad. Because now the big M is what I had L, maybe I should change that M above equation 19 to L. I'm going to track with what was stated in the theorem 3.1. So, all right, so where's the norm of Z minus Z naught coming from? Did you get that?
The norm Z minus Z naught.
In equation 19, like where's that coming from? Do you understand?
That's coming from what we talked about last time, or the last paper, with the one over the R equaling to.
Oh no, it's not. It's actually not that. It's something. It's the mammal theorem.
Oh, from 2 papers.
So
yeah.
the length of an integral
Yeah.
is less than or equal to the submultiplicative constant.
Times the norm.
Yeah, times the bound on the integrand,
Mm-hmm.
which in this case is big M, or if I was sticking with the theorem statement, big L, and then the length of the curve. So this is a line segment from Z naught to Z. The length of that is the length of the displacement vector. So the length of the curve is the norm of Z minus Z naught. That's where that's coming from. So, and then let's see here, lemma. I said that there exists an L greater than 0 such that the norm of f zeta minus v, f zeta minus w is L times that, right? And this, I believe, is from Zorich, which is a beautiful two-volume set of calculus. It starts at like calculus 1, calculus 2, calculus 3, really advanced calculus,
Mm-hmm.
and a lot of deep results in there. But it is meant for introductory students as well. It's kind of interesting. It's written by Russians originally, but it's been translated. So definitely something worth reading as a second calculus book.
Let me go see if I have some more fiber, unless you want to put on a pot of coffee.
I could copy.
Appreciate that.
I just gotta, you don't mind microwave coffee? I think it was made this morning, so we're good. Let's see here. Let's see here. I was meaning to do the same.
I seen 3.2 that looks like the definition of the.
The mean value theorem is not true in higher dimensions. But there's a variant of it. So I just feel like here. Let me show you why that is. If you think about a helix, right? So you can think about. Okay, so like here's the vector to the helix, right? So if you think about dr dt, it's got, if we could do cosine t, sine t, well, excuse me, so cosine. I guess I should have. I mean, this would be, if I use the usual parameterization of a helix, the derivative is this, right? So if I look at, say, so this is t equal to 0, right?
Yep.
And, let's say here, t equals to pi over 2, right?
Yep.
So we look at the dr dt of c equal to r of pi over 2 minus r of 0.
Mhm.
So this would be the average, and so that would be
1, 0, 1, negative 1, 0, and then that'd be 1, 0. Yeah, something.
right. So the point is something. The z components cancel.
Yeah.
Excuse me, the z. I'm an idiot. Z components don't cancel.
Oh no,
Because
it would be
it
t
wasn't
minus
there.
1.
Right. So. Oh, actually, that's 1.
Mhm. You should get.
Oh.
You should get 0, 0, negative 1, t minus 1, I think.
Oh, this is not the right example. Man.
Right? I think that's right.
Son of a gun. Remembering this wrong, Roderick.
Oh. So the mean value
Well,
there. We'll just
if I took, let's take this point instead.
yeah,
Look at t equals 0, t equal to 2 pi.
yeah.
Then r of 2 pi minus r of 0, they've got the same
Mhm.
x components, right?
Yeah.
So this is actually just 0. Excuse me, 0, 0, 2, right? Can that be, does there exist, so you want to say this, right, should be equal to, can that be equal to the change in, can that be equal to 2 pi times dr dt for some choice of time, say t naught, you know? And here, 0 less than t naught, less than 2 pi, that's what we'd like for the sort of naive version of the mean value theorem to hold. If the change, the average change in the function is equal to the instantaneous change, that would be, that's what the mean value theorem says, right?
Yeah, but well,
But what is this? dr dt, it looks like
you'd have to get like a yeah, exactly.
you have to have that 0, but you can't have that 0 because sine and cosine can't simultaneously be 0.
No, and then you'd have to pop out a pi too for the t value. It'd be like 1 over pi, and then that's
Yeah, I mean, if I worked through the details here, we would have come to the same issue, I think. But
yeah.
the point is, no, you can't make the, like, and you can kind of see it if you just look at like the, if you just like think about connecting 2 points like this one and that one, right, and look at the delta r, and then ask, okay, is there any point in between those such that the tangential direction is like a scalar multiple of that? If you could really see it in 3D, you'd see it doesn't track. But anyway, this is a concrete counterexample.
Yeah.
But in Zorich, there's a weakened version of that, which, do you want milk?
I'll just take it live.
Sure.
Yeah, that'll be fine.
Fruit fly?
But just pull it out and don't tell me.
See, that's the advantage of putting milk in it, is that, if you put the milk in it, if there's any kind of fruit fly, they just pop up to the top.
I see what you're saying though now.
Ah. Sorry, I microwaved that and
Well, you could get a
I microwaved that thinking of milk being added to it, so beware. What's that?
Well, you might be able to get a tangential point that is. No.
I'm not.
No, you can't.
No, I'm not saying that it's impossible.
It's just not likely.
like certainly,
Like the way it behaves in Z is just not the way it's going to behave on the tangential.
like certainly there exist curves where the average factorial sense
Mm-hmm.
is equal to the instantaneous rate of change at some point between. For example, a line.
Yeah. Well, I'm just talking about like for the helix. It's just no. But yeah, a line.
But thankfully, Zorich has a theorem which instead of
You could get very close.
instead of giving, this is the next best thing, equation 20 here, it says that the change in the function, f of a plus h minus f of a,
Mm-hmm.
is less than or equal to the norm of h, which is, by the way, that's the displacement between a and a plus h. And the supremum of x from the line segment from a to a plus h, and then taking the norm of the differential of f. All right, and that's the operator norm, by the way. That norm of df, that's the supremum over the unit ball of dfx of w. So this is the sort of thing you run into when you start analyzing issues of convergence and continuity and everything for operators. You have to start looking at this operator norm and making these kind of arguments. But anyway, the point is this equation 20 gives me what I need. It doesn't give me equality, but it does relate the norm of f to the supremum of that df thing, which then ties back into like the partial derivatives with respect to the algebra. Well, let's see how it goes. So the df actually can be written as a linear combination of the differential equation 22 and the line segment from a to a plus h, where h is 0 comma h. That drops out the w naught piece, so I just have the y1 derivatives through yk derivatives like that. I assume that the norm of the partial derivative is bounded by L. I definitely need to get that M earlier in this proof is a typo. I need to fix that. And so there you go, triangle inequality, and some multiplicative constants there. And lo and behold, I've got that the norm of f minus the other f is norm of h, k, l, m, a. All right. Where L is the bound on the derivatives, k is the k in the f is a function from a to upper k. That's that k. And so a submultiplicative constant, right? All right. So there, that's the end of the lemma. So now I proved that. Okay, great. So the lemma was just 3.2 on the previous page, right? Which basically says that given the conditions, the difference in f can be related simply to a constant times the difference of the norms of the v and the w, assuming that the first piece, the zeta, matches up. All right. Now, that is helpful because then I can inductively suppose that this yn minus yn minus 1 is less than or equal to that. All right. By the way, it's true for 1 because I already calculated that back. That was the calculation that was before the lemma. Equation 19. See, equation 19 says that the y1 minus y naught is bounded above by like a constant times the difference of z and z naught, normed. That's equation 19. So the thing we're just looking at is the inductive extension of that, which it turns out you need that constant m l to the n minus 1. All right, great. So equation 27, I look at the difference, I put in the definition of, they're defined by the Picard iteration like that. Lemma 3.2, I am swapping out the f for just the second component, which is the yn and yn minus 1. And then let's see here, by the induction claim, that's less than or equal to that. And let's see here, zeta minus zeta naught to the n, that is the arc length of, that is actually the arc length if you look at it.
Zeta minus zeta naught.
Zeta minus zeta naught to the n times the norm of d zeta, that is a formula for the calculating the arc length to the nth power, because you're going on the line segment from z naught to z. So like a formula for just this straight arc length would be this. If I was just integrating over a curve, right? But this curve is z naught to z. So I'm integrating like length of zeta minus zeta naught. That's supposed to be z naught rather. So if you look at that is the arc length. That's like s going from z to z naught to z. That's what we call arc length. So, but it's to the n power. So this is really s to the n, and this in other notation is just ds. And when that popped out at me, I was like, oh, I can calculate that, because s to the n just integrates to s to the n plus 1 over n plus 1. And but I also know that the arc length of z naught to z is just norm of z minus z naught. And so there you have equation 27, which verifies the induction hypothesis. All right. Furthermore, if s denotes the distance from z naught to z and beta is Messel, then we would formulate the bound of 26 as that. Bound of 26. What was the bound of 26? This guy. Oh, okay. So I made my induction hypothesis. Now I'm cleaning it up by lumping all that stuff together to be beta. All right. And so, right. Okay. So, since I is compact, we know that there exists an S naught such that the norm, that means it's closed and bounded, and so that means that you can only get at most distance S naught away from Z naught. And let's see here. So that gives me, now I let beta naught be MALS naught. I got that. Alright. But what else do I know? Beta naught to the n over n factorial, that's e to the beta naught.
Yeah,
That is a convergent series.
it is.
Yeah. And m over L times that is still a convergent series. So that right there, equation 29, I have bounded the difference, the norms of yn and yn minus 1 by a term, which is the term of a convergent series. So by the majorizing theorem, Weierstrass test basically,
Yeah.
I get uniform convergence of the successive differences and therefore uniform convergence of the original y sub n as defined by the Picard iteration. And then of course it remains, so that gives you the existence of a solution.
Yeah.
Now then the question is, why is that a solution to the initial value problem? I guess there's something else here, like how do I know that solves, I mean, okay, great, I've constructed this sequence of functions. How do I know that that sequence of functions actually solves the given differential equation?
Well, because if it converges, I mean, it has a limit, right?
Yes, but why should that have anything to do with the given differential equation, which was
If it's not differential.
y is dy dz?
Well, I think because if you can prove differentiability, and then you can find a
let me put the cards on the table here. So I'm asking why have we solved this? How are we defining that thing? The Picard iteration, yn plus 1 of z is w naught, right? Plus what? V naught to z of f of what was it? Zeta. Yn of zeta. Star e zeta. No, we're not claiming that. Well, maybe are we claiming that solves? I mean, so what happens if you differentiate this with respect to zeta, z rather? That's 0, right? It's a constant.
Yeah, and that just spits you back out. That same thing is disintegrated.
All right, because the fundamental theorem of calculus part 1 we saw in the first paper says that when you differentiate this thing, and the this has no z dependence. This z is not the same as this zeta is the integration zeta.
Yeah.
This z is something else. So like you said, you just evaluate at z.
Yeah.
Right? So that also doesn't quite fit the bill.
Wow.
Well, to solve this differential equation, we need y here, and we need y here. I have yn plus 1 here. I have yn here. So that doesn't make yn plus 1 or yn technically a solution to the differential equation. However, as n goes to infinity, what happens?
Oh, they both have the same thing, convergence, yeah.
Right, so in the limit, if we take y and going to y as n goes to infinity, or we could maybe call it phi instead of phi, then that limiting function, or you call it y sub star, I sometimes call it y sub star, that limiting function, that's the one that solves the differential equation. So the Picard iteration is set up so that its limit point, if there is a limit point to the recursion, right, that limit function will be a solution to the differential equation. That's the whole idea of 16. And the thing is, we just proved the uniform convergence of the sequence. Consequently, the limit function does exist. Furthermore, since the we can also argue properties of the limit function follow from the properties of the function because we assume that f is a differentiable, so consequently the limit function is a differentiable. The uniqueness still a question, right? So that's where we are here on. Oh, actually, so I guess 30. I show that the limit y star at least has y star of z naught equal to w naught, so it solves the initial condition. And then I think I'm going through here in 31 and